So this is part 2 of dealing with Chapter 7 practice problems. This is for Section A of the chapter, okay? And in part 1, I covered what all these formulas represented. So if you don't know where I am, you need to click on that video in order to view it, because I did not cover all the problems to solve with it. Okay, but these formulas, certainly they would be on the quiz, the test, the final exam, all that other stuff. I would want you guys to have the formula, but I also want you guys to know how to be able to use it. Okay, in the first part we talked about changing radians into degrees and vice versa. We talked about the idea of angular speed. Remember, you've got two different units of angular speed. One could be degrees per second. That's one way to look at it, and the other is radians per second. Okay, so with that, we also talked about angular acceleration. With angular acceleration, guys, you are looking at how fast is the angular speed changing per second. So what you end up getting is radians per second, or radians per second squared. Now, could you do this for degrees per second, or degrees per second squared? Yes. You actually could. Okay? So I rushed through this problem on the last part, so I just wanted to go through here. You have a toy plane on a string that goes around 3 complete circles in 9 seconds. Okay? What is the angular velocity? Well, if you think about it, that angular velocity happens to deal with the change in the radians divided by the change in the time. This is pretty similar to when we look at linear motion, when we talk about velocity, which is the change in distance over the change in time. But that's a linear thing. Here we're looking at a circular thing. But the idea is still the same. Okay? So with that, okay, I got my time. I've got my delta t right here, about 9 seconds, but I don't know my radians. But they did give us a big clue. And that clue, ladies and gentlemen, is 3 complete circles with the toy plane. So you're swinging it 3 times. So that means you made 3 complete revolutions. Now, if you guys remember, 1 revolution is equal to 2 pi radians. Okay? So if we have 3 complete revolutions, then it would be 6 pi radians. So when we are looking here at our angular velocity, okay, 2 pi times 3 gives us 6 pi radians over 9 seconds. Okay? So when we go and finalize the thing, okay, you'll notice it'll be 0.667 pi radians per second for that. Okay? Now I kept the pi in there. If you wanted to convert the pi, you can use that as 3.14. That also works, but in this case I left the pi here just to remind me that this is a radians type problem. Okay, let us move on here. Oops, there we go. So, our next problem here, we have a satellite is orbiting the Earth at 0.00087 radians per second. How long will it take to circle the entire world? Okay, let's see some things here. So this, guys, this is our angular speed. Okay, it's a very slow angular speed, but it is an angular speed nonetheless. We're looking at here, how long will it take? So they're asking us for our time. How long is it going to take? And then the question is, well, wait a minute, how much did it travel? Well, it circled the entire world. Since we're dealing with radians, then that means it's 2 pi radians for circling the entire world. Okay? Now, that being said, we have our 3 pieces. Now, this kind of looks familiar. You might think about an earlier chapter. We looked at linear motion, okay, where we talked about the velocity is equal to, okay, and then we have the time, and we have our distance, okay? So if you look at it, we can use the formula here that our angular velocity is equal to the radians that we have, the change in the radians over the change in time. Okay, now we're trying to find time. Easiest way to do this is go ahead and do the algebra thing, where you can literally flip these. You say, wait, what do you mean by flip? Well, if I went ahead and multiplied both sides by delta t, okay? If I multiply both sides by delta t, guess what? This goes away, okay? And now we have delta t times angular speed is equal to the change in radians, but we're interested in delta t, so then we can go ahead and say delta, our change in radians divided by angular speed.
Dude, I have no idea what this thing is.
I am filming this in front of a live audience, in case you are not aware of it, okay? Good job, Michael! You're on the internet, buddy! Woo!
Yeah.
Michael Perez. Michael Perez costs 2020, baby.
Okay, so, alright guys, so that's the formula that we would end up using for this. Now, for some people, they would just go ahead and plug it in and solve for t that way. That's fine. I just went ahead and showed you how the formula works out, okay? So there's more than one way to do this. So I know that I have got 0.00087, and that's going to be on top of 2 pi radians, because it's one circle over the world. Okay, we're looking for time, and there is our speed. So I'm not going to finish it off, except you guys know this is going to be a very large number. It's going to take a long time for this satellite to circle around the planet. Okay, let's go ahead and let us move on. In our next problem here, we have a toy plane on a string accelerating from 2.1 radians per second to 3.1 radians per second. What is its angular acceleration? Well, there's a little bit of a problem because you're missing time. So for the sake of argument, we're just going to say all this is happening in 1 second. Okay? So when we're looking at the acceleration, that is the funny looking alpha there, and that's going to equal, okay, that's going to equal the change in our angular velocity over the change of time. Well, wait, what do you mean by angular velocity? Well, the angular velocity is how fast is our toy plane traveling. Now, in this case, here is our initial angular speed. Here is our final angular speed there. So typically, when we go with the delta angular, we go WF minus WI, which in this case, ladies and gentlemen, should be a big whopping 1. So 3.1 minus 2.1 divided by 1. And I'm going to let you do the math. Now, what are the units here? This is an acceleration type problem. So that means it's going to be radians per second squared, or radians per second per second. Both of these mean the same thing. Keep that one in mind. Okay? And with that, ladies and gentlemen, we have a series of problems here that they are the same type of problem, except we change the numbers a little bit. I am not going to have the time to go over every single one, but the idea, I put that down so you guys can see what is that going to look like. How is that centripetal acceleration going to change if we vary something like the velocity or tangential speed and the length of the sling from hand to stone? Okay, that'd be kind of an important thing. But maybe the first question, okay, well, let's take a look here. So David is trying to hit Goliath with a 30-gram stone thrown from a sling. As he swings the sling horizontally over his head in a circle, the stone has a tangential speed of 5 meters per second. The sling is 1 meter long from hand to stone. What is the magnitude of the centripetal acceleration of the stone? Well, maybe the first question is what's up with this tangential speed? Does the mass of the stone have anything to do with this? And what's up with this 1 meter long length from hand to stone? What is up with that? Okay, well, let's take a look here. What is exactly centripetal acceleration? Well, if you look at it, centripetal acceleration is that force, that acceleration that's guiding our rock toward the center of our circle. Okay, that's our centripetal acceleration. How fast is it doing that? Okay, our tangential speed, on the other hand, if we look at a circular motion, if you have an object at the edge of the circle, okay, it's going to go at a certain angular speed, which means it's also going at a certain velocity in a straight line, but it's always tangent to the edge of the circle. And this, when we talk about something like this, when it's a tangent like this, that's how we call it the tangential velocity. Okay, so that's what it means there. Because remember, the fact is that the rock is turning in a circle. That means the acceleration is going to be changing, and so will the velocity be changing as well, because it's shifting direction every microsecond. Okay? So with that idea, guys, now we're going to go ahead and we're going to try to solve the problem. First, let's see, do we have any important formulas that would be useful to us? Yeah, we do. We have centripetal acceleration, so here it is. The change in our angular speed over the change in time. Okay. We also have a radius thing going here, and that's our centripetal acceleration also. So that's angular acceleration. This is centripetal acceleration. This is the one we really want, okay, because this is tangential velocity. So that's what we need, and R is short for our radius, okay, from the hand to the stone, okay, as you're slinging this around. Okay, so VT squared divided by R. All right, so let's go ahead with it. So our basic formula is VT squared divided by R is going to give us our centripetal acceleration. So that's the formula we're going to be using, ladies and gentlemen. So with that, folks, we're going to go ahead. Our tangential speed, they gave it to us. They gave it to us as 5 meters, okay, per second. So that's going to be squared, so 5 times 5, okay, or I'm just going to make this a whole lot easier and say 5 squared divided by the radius. Well, we looked at this one here, 1 meter for that, okay, and our centripetal acceleration is going to be 25 meters per second per second. Okay, that is our centripetal acceleration. Now, when you look at the next problem, same exact thing. Okay, same 5 meters per second. Okay, tangential velocity, but we changed the radius here. Instead of a 1, now it's a 5. Okay, that's a terrible looking 5. Okay, so in other words, it would be 25 divided by 5, or 5 meters per second, or 5 meters per second squared. Okay, so the other problems that you're seeing on the paper, we varied some factors, and some people may be thinking, wait a minute, what about that 30-gram stone? Does it make a difference? Not for this. Not for this, ladies and gentlemen. And with that, we've come to an end about the Chapter 7, Part A, looking at how to solve some problems for the problem set. I hope it benefits you guys. Good luck, God bless you, and take care.
See ya.